Hi, Matthias from 10 Minute Physics here. Welcome to tutorial number 20. Today I'm going to show you how to write a 3D water simulator and the interaction of water with objects in under 100 lines of code. Here is my water simulation. As you can see, we have a tank and 3 balls interacting with the water. The density of the yellow ball is larger than the density of water, so it sinks to the ground. The densities of the orange ball and the red ball are lower than the density of water, so they float on the surface. Since the density of the orange ball is larger than the density of the red ball, it is more immersed in the water. I also implemented a refraction effect of the water surface. As usual, I wrote this demo in JavaScript, so it runs in any browser. I put the direct link to the demo into the description so you can immediately play with it. For the demos and the slides of all my tutorials, have a look at my webpage. Let me now explain the method that I used to implement this simulation. I represent water as an array of columns. We can do this on a line or in the plane. If we use a line, we call this a 1.5 dimensional simulation. This is because we have a 1-dimensional line, but the columns poke out of this line. If we use a plane, then we call this a 2.5 dimensional simulation. This is because we work on a 2-dimensional plane, but the columns poke out of this plane. There is a variety of advantages when representing water as columns. First, it's very simple to simulate. Second, we get a fast simulation. And third, it's easy to extract the water surface. There are also a few disadvantages. We cannot simulate overturning waves, and we don't get splashes. We can, however, add this effect by using an additional particle simulator. The grid setup is very simple. Each column stores a height and a velocity. Both the height and the velocity are needed to get a dynamic simulation. We use the same width S for all the columns. To derive the simulation method when using water columns, we need Archimedes' principle. The principle says that any object totally or partially immersed in a fluid or liquid is buoyed up by a force equal to the weight of the fluid displaced by the object. If we have two water columns next to each other with the same height and velocity 0, then we expect nothing to happen. So let's assume we have two adjacent water columns with different heights, h1 and h2. In this situation, we can think of having a balloon here. Now the question is, what's the force acting on the balloon? From Archimedes' principle, we know that the force is proportional to the volume of the balloon. The volume of the balloon is proportional to h2 minus h1. This means the force acting on the balloon is proportional to h2 minus h1. From Newton's second law, we know that the acceleration is proportional to the force. From the conservation of volume, we know that if the column 1 is accelerated upwards, then the column 2 must be accelerated downwards by the same amount. So the acceleration of the second column, h2, is minus h1. Now let's have a look at what happens when we have a column I surrounded by two columns I minus 1 and I plus 1. Now to compute AI, we need to consider both neighbors. In the pair I and I plus 1, the column I plays the role of the left column, as in the slide before. Therefore, AI is proportional to hi plus 1 minus hi. In the pair I minus 1i, the column I plays the role of the right neighbor. Therefore, we have a minus sign here. Removing the brackets gives AI is proportional to hi minus 1 plus hi plus 1 minus 2hi. Saying a quantity is proportional to another quantity means that the quantity is equal to k, the constant of proportionality, times the other quantity. In our case, AI is equal to k times hi minus 1 plus hi plus 1 minus 2hi, where k is a constant. From the discretization of the wave equation, we can actually derive what the meaning of this constant k is. K depends on two other constants, c and s. The constant c is the wave speed and s is the column width. Here is the situation of a 2.5 dimensional simulation. Now a column ij is surrounded by 4 neighbors. The equation to compute the acceleration of the column ij is very similar to the formula we got for the 1.5 dimensional simulation. The acceleration of column ij is proportional to the sum of the heights of all the surrounding columns minus 4 times the height of the column itself. The constant of proportionality turns out to be exactly the same as in the 1.5 dimensional simulation. C squared over S squared, where C is the wave speed and S is the column width. There is one last problem we have to solve before writing our simulator. The problem is that when column ij is on the boundary of the domain, then we access a column outside of the boundary. There is a very simple solution to this. If we want to simulate reflecting boundary conditions, then when accessing a column outside of the domain, we just use the height of the column ij itself. Now we are ready to write down the algorithm to simulate a 3D water surface. It's extremely simple. It consists of 2 loops over all the columns in the domain. In the first loop, we first compute the acceleration of each column. We use the formula we just derived before. Then, given the time step delta t, we can update the velocity of each column by adding delta t times the acceleration. Then, we loop again over all the columns and update the heights. We update them by adding delta t times the velocity. In this case, we used the semi-implicit Euler integration with time step delta t. To get a stable simulation, we have to make sure that waves do not travel further than 1 grid cell in one time step. Now let's see how we can simulate the interaction of objects with the water surface. We want to have two-way coupling. This means we want to know how objects influence the water surface and how the water influences the objects. Let's first have a look at how the objects influence the water surface. Here's a very simple way to do this. We simply push down all the water columns such that they don't intersect with objects. The first problem is volume loss. The second problem with this approach is that it doesn't work for fully submerged bodies because we get this void here. Here's my own solution. I use an additional field B. As before, H stores the height of each column. The value B stores the height covered by objects. Now I add a third loop over all the columns in the simulation algorithm. First, I compute the change of the values of B between the current time step and the previous time step. I then add the change of B to the heights of the water columns. This change can be positive or negative without bias, so volume is conserved. The constant alpha is the number between 0 and 1 and defines the intensity of this effect. It's important to smooth the B field to prevent spikes and instabilities. Now we need the opposite direction as well, how the water surface influences objects. For this, we use Archimedes' principle again. The force acting on the object is the same as the weight of the water replaced by the object. We can compute the weight as m times g, where g is the gravitational acceleration. The mass is the density of water times the volume. The volume is O times s squared, where s is the width of the column. This means that for each overlap of an object with a water column, we add this force to the object at the position of the water column. I use a very simple method to render the refraction effect on the water surface. Let me first show you how to render a fully transparent plane. Of course, the simplest way to do this would be to just not render anything. But there's another method to do this. We first render the scene behind the plane to a texture using the current camera. Then to render a fragment of the plane, we use the screen coordinates of this fragment to look up the color in the texture. Now there's a very simple way to get the refraction effect. Now we use the screen coordinates of the fragment plus an offset to look up the texture color. We make this direction dependent on the surface normal. The length of this offset is dependent on the distance of the camera to the water surface. Now let's have a quick look at the code. I implemented a class called water surface. Here is the constructor. The actual simulation starts at line 170 with the simulation of the coupling between bodies and the water surface. Here you see the method to simulate the surface itself. And this is the simulation loop. It ends at line 270, so we have exactly 100 lines of code as promised. As you can see, the method to simulate the surface itself is really very simple. I run through all the water columns, compute the sum of the heights of all the neighbors, and subtract the height of the central column itself. I multiply this quantity by the time step dt and add it to the velocity. In the second loop, I add the velocity times dt to the heights. This is a fragment shader for the water surface, and this is the most important line here. UV are the texture coordinates to look up the color in the background texture. I use the screen position of the fragment, but now add r times the normal of the water surface. For r, I should actually use the distance to the camera. However, in my very simple implementation, I just use a constant. For simplicity, I also render the entire scene and not just the scene behind the plane. So the challenge for you is to fix these two problems. If somebody finds a very nice solution, please send me a pull request on GitHub. This concludes the tutorial. I hope you enjoyed it. Thanks for watching, and I see you in the next one.